Hello there, and welcome to Life Beyond Seen, the little corner of calm where curiosity softens at the edges and science settles into something gentle enough to drift alongside. Tonight we're heading somewhere ancient, somewhere that existed long before our calendars, cities, or footprints. A place that carried its own stories in salt and shadow long before the first human ever wondered about the world. We're going into the oceans of the past, the ones that once belonged to creatures people now call sea monsters. They weren't monsters in the fairy tale sense, of course. They didn't lurk in the darkness waiting to startle sailors or snap ships in half like the legends suggest. They were simply animals shaped by an earth that looked nothing like the one you and I know. And yet, the idea of them still sends a quiet shiver of fascination through the imagination. Not fear, not dread. Just that strange awareness that the ocean has always been home to lives so different from ours that they almost feel unreal. Before we dive into that deep blue history, I'd love to know something simple about you. Where are you listening from tonight? Are you near the coast or somewhere far from the sea? Maybe you're on a quiet street with the sound of a late bus rolling past, or in a bedroom where the world has gone soft and dim. And I wonder too what time it is for you right now. There's something oddly fitting about exploring ancient oceans while each of us sits in our own moment in time, scattered across different cities, countries and hours. It gives this journey a sort of shared quiet, even though none of us are in the same place. If you find this soothing, or if it helps you unwind a little, I'd be grateful if you'd consider liking the video or subscribing. It helps this little space find others who might want to drift along with us. So, take a slow breath in, let your shoulders relax, and settle in. The oceans we're about to explore were vast, wild, and filled with creatures that would seem unbelievable if we hadn't found their bones. And the water itself was different. Its temperature, its chemistry, its light, even its sounds were shaped by a planet still experimenting with its own form. That's the strange thing about imagining the distant past. We tend to picture it as just an earlier version of what we see today, maybe with bigger creatures or slightly different coastlines. But the truth is that the oceans have changed as often as the land has, and sometimes in ways that are hard to wrap your mind around until you sit with it for a moment. Imagine, for instance, standing on a shore millions of years ago. The air would taste unfamiliar. The position of the continents would be all wrong. And just beneath the waves, the water might hold animals that could glide silently for incredible distances, with bodies streamlined in ways no fish or whale has today. Some of them had flippers that worked like wings, carved for long, steady movement. Some had long necks that bent and swayed through the water like living periscopes. Some had jaws shaped for biting through shells, or slicing through enormous prey with movements that looked almost effortless. These were not the oceans of coral reefs and gentle shoals that we know now. They were worlds that never stopped shifting, and the animals that lived in them changed just as quickly in order to survive. But before we talk about those animals, it's worth pausing to think about the oceans themselves. Not the stories we've imagined about them, but the real water, the real world beneath the surface. The ocean is not simply a container where animals live. It is a constantly moving body that shapes life as much as life shapes it. Temperature, salinity, oxygen levels, currents, coastlines, the depth of the sea floor, volcanic activity, the minerals drifting through each layer of water. All of these things decide what kind of creatures can exist at any given moment in Earth's history. So to understand what the ocean was like in the time of sea monsters, we have to understand the planet they lived on, because nothing in the ocean exists separately from that larger story. Millions of years ago, the Earth was warmer than it is now, much warmer. The poles weren't covered in thick ice. Some periods had no ice at all. That meant sea levels were higher and coastlines stretched far inland across places where cities and forested mountains stand today. Entire regions we now think of as dry land, plains, deserts, farmland, towns, were once part of shallow seas, warm, wide, sunlight-filled waters that created perfect conditions for large marine reptiles to thrive. The warmth didn't just exist on the surface, it soaked deeper, shaping layers of water that were comfortable for cold-blooded animals in ways modern oceans rarely are. Without ice caps, without the dramatic temperature gradients we live with today, the ancient oceans would have felt strangely even in their warmth, almost like the entire world was caught in a kind of extended summer. This steady warmth also affected ocean currents. The circulation patterns we know today are driven in part by differences in water temperature and salinity between the poles and the equator. But when the poles were warm and the global climate was more uniform, those differences were much smaller. Currents moved differently, some were slower, some were broader. Some flowed in directions that no longer make sense with the continents rearranged to their modern positions. These shifting pathways carried nutrients and life across vast distances, allowing creatures to travel and evolve in ways that wouldn't be possible now. You could think of the ancient ocean not as a single blue expanse, but as a series of connected environments constantly negotiating with heat, light, and movement. The chemistry of the water played a role too. The balance of oxygen and carbon dioxide has swung back and forth countless times through history, changing the way animals could breathe underwater and how easily they could grow large. There were periods when oxygen was abundant, making it possible for marine reptiles and fish to reach enormous sizes, and there were times when certain layers of the ocean became oxygen poor, creating vast stretches of dark water where only specialized life could survive. These oxygen levels also influence the appearance of many animals. For example, when oxygen is abundant, bodies can grow thicker, muscles denser, and metabolism more efficient. When oxygen is scarce, animals must become slower, more cautious, shaped instead for endurance or survival in low-energy environments. The ocean floor was shifting constantly too. Volcanoes erupted beneath the waves. New crust formed and pushed older crust aside. Trenches deepened. Mid-ocean ridges rose. The noise alone would have been different from what we imagine. More rumbling, more crackling, more deep vibrations that travelled through water in ways our ears have never heard. And with each geological shift came new coastlines, new habitats, new opportunities for life to spread or vanish. All of this matters because when we picture the so-called sea monsters of the past, it's easy to focus only on their shapes, their teeth, their size, or the way they might have moved. But those things didn't appear out of nowhere. They were answers to the oceans themselves. The bodies of these creatures were essentially shaped by the physics and chemistry of ancient seas. The water carved them into the forms that made sense for their time, much like wind shapes, dunes, or rivers shape their own beds. And just as the modern ocean shaped sharks, whales, and seals, the ancient ocean shaped plesiosaurs, mosasaurs, ichthyosaurs, and countless others that once dominated waters across the planet. If you picture one of these animals swimming, imagine the water it moved through as carefully as you imagine the creature itself. The density of the water, the warmth, the presence of plankton drifting in thick clusters, the faint light filtering down, the sound of distant currents rolling along the edges of broad continental shelves. The water was alive with more than just the big reptiles. There were ammonites spiralling through the depths with their coiled shells. There were giant fish with armoured heads and powerful jaws. There were delicate ribbon-like animals drifting near the surface, where sunlight scattered into shimmering patterns. And somewhere below all of that, in the deeper, darker areas of the sea, there were creatures that have left behind almost no fossil record because their bodies were too soft to be preserved easily. The ocean at that time was as crowded with life as it was with possibility. But even with all this life, the ancient ocean still had a quality that might surprise you. It wasn't chaotic. It wasn't a constant battle of creatures lunging at each other. Most of the time, it was calm. Ocean life, even large ocean life, spends most of its time simply moving, feeding, conserving energy, and existing in the steady rhythm of the water. When we imagine sea monsters, we often picture them in the middle of some dramatic moment, jaws wide, fins slicing forward, tails whipping through foam. But the truth is that much of their lives would have been spent cruising through the water with a kind of practical stillness, gliding without hurry, following the paths carved by warm currents or the routes shaped by migrating prey. That is where our journey begins, not in the excitement or the teeth or the spectacle, but in the ocean itself, in the warm, shifting, living waters that shaped creatures whose bones now lie in stone, waters that once covered vast parts of our world and carried entire ecosystems across continents that hadn't yet become familiar, waters that held stories we're still trying to uncover one fossil at a time, and as we move forward we'll let this image guide us. Not the fearsome legends or the exaggerated drawings from old adventure tales, but the real ancient seas, their warmth, their movement, their quiet power. Because understanding those waters is the first step toward understanding the animals that lived within them. When people imagine ancient oceans, they often picture the creatures first, the ones with long jaws or powerful tails, or eyes that seem too large for their heads. But before those animals ever swam through the water, the world itself had to become something they could survive in. The oceans of the past didn't just look unfamiliar, they behaved differently. The surface, the chemistry, the light, even the atmosphere above them gave the water traits that shaped life in ways that don't match anything we see today. In the long timeline of Earth, the oceans have been many things, and some of their earlier versions were so changed that if a modern person stood beside them, they might not immediately understand what they were looking at. The colours would be slightly off. The heat would feel surprising. The coastline might stretch in a direction that doesn't line up with anything on a modern map. These oceans wore different skies, not only because the continents were in new positions, but because the air above them carried a different balance of gases that influenced everything beneath. To understand what that meant, imagine standing on the edge of an ancient shoreline during a warm period of Earth's history. There were several such times, and each had its own character, but they shared certain broad traits. The air would feel thicker, not in an uncomfortable way, but in the sense that it held more moisture. Temperatures ran higher across the planet. There were eras when palm trees could grow near the poles because the climate allowed it. With fewer ice caps and warmer global averages, sea levels rose until vast areas of modern land were completely underwater. The shape of the continents wasn't the same either. They moved, collided, stretched apart, and rearranged coastlines in a slow but constant cycle. Some of the seas where marine reptiles lived existed in areas that are now deserts or plains. If someone from the modern world were able to stand there, they would notice that the horizon looked slightly different. The sky's colour could shift depending on volcanic activity, atmospheric composition, and the amount of dust carried by winds that swept across continents not yet settled into their modern positions. These differences in the sky didn't just change the view, the atmosphere influenced the oceans directly. Levels of carbon dioxide were often higher. During some periods, they were much higher than anything humans have experienced. This trapped heat more efficiently and warmed the planet. Warmer air meant warmer oceans, and warm oceans behaved in ways unfamiliar to modern observers. Today, we associate warm water with coral reefs, tropical storms, and colourful fish. But the ancient warm seas were even more extensive, spreading across entire regions where modern climates would never allow such conditions. Without polar ice creating sharp temperature contrasts, ocean currents slowed or shifted into unusual configurations. Instead of strong cold currents pulling nutrient-rich water upward, many areas would have felt more uniform. The difference between the surface and the mid-level waters could be much smaller than today. This allowed certain animals to occupy depth they might now avoid, simply because the temperature was comfortable across larger zones. The colour of the water itself could appear different. This wasn't due to anything mystical, just the chemistry. At times, when plankton populations surged, the water might take on a greenish tint across enormous stretches. In other eras, when minerals from volcanic activity drifted through the currents, the water could show different shades under certain lighting. These shifts weren't dramatic enough to make the ocean look alien, but they were noticeable when compared to the modern world. If someone accustomed to today's oceans were placed in one of these warm ancient seas, they might describe the water as slightly heavier or slightly murky even in areas with plenty of sunlight. Minerals, dissolved gases and microorganisms created combinations that don't perfectly match any single modern ocean. One of the most significant changes during these eras was sea level. With less ice on land and higher global temperatures, water expanded and spread farther inland. Entire inland seas formed on continents. These shallow bodies of water could stretch for thousands of kilometres, connecting coastlines that are now separated by hundreds of miles of land. These seas weren't deep. Many were only a few hundred metres at their deepest points, but they were warm, well lit, and rich in life. Their broad flat shape created the perfect conditions for marine reptiles, large fish, ammonites, and countless other creatures to thrive. Instead of sharp drop-offs into deep trenches, many shorelines sloped gradually into calm basins that supported entire ecosystems. These regions acted like natural highways. Animals could travel easily between what are now distant countries, simply by following long corridors of water that cut through the continents. Sunlight played a different role too. In warm, shallow seas, light penetrated farther. The surface could feel bright for much of the day, and deeper layers that are dim in modern oceans might have been well lit enough for animals with large eyes or long necks to see clearly. For creatures like plesiosaurs, which had eyes adapted for good underwater visibility, this meant they could hunt or navigate in broader regions of the water column. Light distribution influenced everything from plant-like microorganisms to predators near the surface. Large marine reptiles benefited from these conditions because they could move through well-lit areas more confidently. Their prey, too, adapted to the availability of light, shaping their behaviour in ways that would make little sense to a modern biologist, unless they understood how bright these ancient waters could be. The air composition shaped weather differently as well. Warmer periods of Earth's history saw more frequent storms, but these storms weren't necessarily harsher, they were simply more common. Rainfall patterns shifted across continents in long cycles, influenced by ocean temperatures and currents. This meant that runoff from rivers carried different minerals into the sea, changing nutrient levels and influencing where plankton and small animals gathered. Areas near ancient coastlines might have experienced blooms of life, attracting larger creatures and creating feeding grounds that supported entire generations of marine reptiles. In some eras, the wind carried fine dust from vast inland deserts that didn't exist yet in their modern form. This dust carried iron and other minerals that fertilized parts of the ocean's surface. Plankton used these nutrients to grow rapidly, which in turn supported fish populations, which supported larger predators. These environmental cascades formed the foundation of ancient marine ecosystems. The world above the ocean shaped the world within it, sometimes more dramatically than one might expect. The position of the continents also influenced how these oceans behaved under their different skies. During times when continents clustered together into supercontinents, the oceans behaved differently than when those landmasses split apart. Large inland bodies of water formed in the cracks between separating landmasses, creating unique environments that don't exist today. When continents were together, the oceans could form a single massive body with long current systems that circled the world. These currents moved slowly, distributing heat in ways that made the entire planet feel more balanced in temperature. When continents drifted apart, those currents broke into smaller systems. This created more variation in temperature and movement, but during the time of marine reptiles, the Earth often leaned toward warmth and stability, rather than the sharp contrasts we recognise today. Because the climate was warmer overall, many ancient oceans were more stable in temperature across seasons. There were shifts, of course, but they tended not to be as severe as modern seasonal differences. Animals didn't need to migrate long distances to stay within comfortable temperature ranges. Instead, their movement patterns likely followed prey availability, breeding needs, and changes in water chemistry. This stability might explain why so many large predators grew to impressive sizes. A steady environment supports steady food chains, and steady food chains allow animals to reach large sizes without running into sudden shortages that could threaten their populations. Even with all this warmth, ancient oceans weren't calm in the sense of being predictable. They changed constantly over long periods of time. The skies above them shifted as volcanic eruptions filled the air with ash or released gases that influenced climate. Some eruptions were so large that they altered ocean chemistry for centuries. Under these darker skies, surface temperatures dropped temporarily, creating short-term imbalances that affected marine life. Yet, in the broader timeline, the trend returned to warmth, and the creatures adapted to these cycles. Fish behaved differently under these skies as well. Some species evolved to thrive in warm, shallow seas, while others adapted to mid-level waters that stayed warm year-round. Large marine reptiles responded to these opportunities, shaping their bodies to match the environment. Ichthyosaurs, for instance, developed streamlined shapes that allowed them to move quickly through open water. Mosasaurs grew long, powerful bodies suited for hunting in warm seas with abundant prey. Plesiosaurs evolved necks of varying lengths depending on their hunting strategies, and those strategies existed because the environment offered so many different niches. Without extreme cold zones or strong thermal barriers, animals could cross vast distances without needing special adaptations for temperature shifts. The soundscape of these ancient oceans would feel unusual to a modern listener too. With different wind patterns, varying continental arrangements, and more active underwater geological features, the background noise would include deep rumbles, steady vibrations from shifting plates, and long travelling echoes. Sound carries differently in warm water. It can move faster and farther, allowing animals to detect movement over great distances. Predators might have relied on sound as much as sight, using the acoustics of their environment to track prey or navigate. The skies above these oceans also supported different kinds of airborne life. Some eras saw flying reptiles soaring above the waves, hunting fish near the surface or gliding long distances on warm air currents. Their shadows occasionally passed over marine reptiles swimming below, creating brief flickers of light on the surface. These interactions weren't dramatic, but they added another layer to the structure of ancient marine life. The sky, the surface, and the water were part of the same system, connected more closely than we sometimes realize. When we think about all these details together, it becomes easier to understand why the ancient oceans produced such remarkable creatures. The warmth, the depth, the chemistry, the movement of water and the sky overhead created conditions that encouraged life to grow large, varied, and adaptable. These oceans didn't just host animals, they shaped them at every level. Long before anything with a human face ever stood on a shore and wondered what might be swimming in the distance, the oceans were already crowded with life. Not in the way people picture them now, with familiar shapes like tuna, dolphins, sharks, or whales, but in forms that looked nothing like anything we recognize today. If you could visit one of these oceans, you wouldn't just feel out of place because of the creatures around you. The entire logic of the ecosystem would feel different. Instead of the fish you know, you'd see bodies that seemed unfinished or assembled in ways that defy modern expectations. The world before fish became the animals we name and classify today was a world full of experiments, with nature testing dozens of designs at once, only letting some survive long enough to become ancestors of the creatures we recognize now. It's easy to forget how long oceans existed before familiar fish dominated them. Tens of millions of years passed with oceans that supported completely different communities. Some of the things we consider basic today, schools of fish moving together, sharks following migrations of prey, reefs filled with vibrant activity, weren't part of these older seas. They had their own systems, their own rhythms, and their own cast of characters. When people think of prehistoric oceans, they often focus on the large marine reptiles. But even before those creatures appeared, the oceans had been building their own history through countless cycles of life and change. To understand this world, imagine starting at the surface. The sunlight above would shine onto waters full of drifting organisms that form the base of the food chain. Some of these organisms resembled modern plankton, while others were stranger. Their shapes weren't streamlined. They didn't need to be. Many simply floated, relying on water movement to bring nutrients to them. These drifting creatures supported everything above them in the chain. Their abundance or scarcity determined whether larger animals thrived or struggled. When the oceans were rich with them, life expanded. When they declined, entire groups of animals suffered. Moving slightly deeper, you'd encounter creatures that didn't fit into modern categories. Some early fish-like animals lacked jaws. Their mouths were simple openings that they used to filter food. They didn't have the mobile, powerful jaws that modern fish use. Because of this, their feeding strategies were limited. They relied on soft foods and small particles in the water. Yet despite their simplicity, these early jawless creatures dominated the oceans for a long time. They filled roles that early ecosystems needed without competing with the later jawed predators that eventually replaced them. These jawless forms came in various shapes. Some were thin and eel-like, sliding through the water with movements that looked slow but efficient. Others had armoured plates around their heads and bodies, almost as if the ocean had decided to produce creatures wearing rigid suits for protection. These plates didn't appear for decoration. They developed because the ocean, even in these early eras, had plenty of threats. Some threats were tiny, such as parasites or small predators with teeth sharp enough to pierce unprotected skin. Some threats were larger, such as early fish with bony armour of their own that used slow but forceful bites. Protection became a way to survive long enough to reproduce, so armour thrived until new forms of mobility and flexibility outcompeted it. This world also held creatures with body plans that vanished long before humans ever walked the earth. Some resembled flattened discs with undulating edges. Others had branching appendages that helped them glide or steer as they hovered above the sea floor. Many had eyes positioned in unusual places because their feeding habits required it. Some looked downward constantly. Others scanned upward. Still others had eyes on the sides of their heads so they could detect threats from both directions. The ocean was filled with animals responding to a wide variety of problems, and each solution looked different from the others. Predators existed here too, but they didn't resemble modern fish. They had jaws that were only beginning to develop, or they had specialised plates that clamped down on prey instead of sharp, flexible teeth. Their movement through the water wasn't sleek. It was deliberate, relying on methodical propulsion rather than quick bursts of speed. But they were still effective hunters. Prey animals learned to avoid certain silhouettes or stay away from the shadows of creatures drifting above them. Some prey developed thicker armour. Others evolved bodies that allowed them to bury themselves at the bottom, leaving only their eyes exposed. Camouflage also began to appear in simple forms, helping creatures avoid becoming meals. As time passed, new groups of animals entered the oceans. Jawed fish began to appear, and this changed the ecosystem dramatically. These early jawed species weren't yet like the fish familiar today. They were heavily armoured, thick-bodied, and often slow. But the presence of jaws allowed for new forms of feeding. Animals could grasp, crush, or tear in ways that jawless species could not. This changed every part of the food web. Prey animals adapted, predators adapted. The entire structure of marine life shifted over millions of years as different species tried to find stable roles within these expanding ecosystems. During some periods, the oceans filled with armoured predators known for their broad heads and crushing bites. They weren't fast, but their strength made them formidable. Prey animals evolved new defensive strategies. Some became smaller and quicker, darting away before predators could catch them. Others grew thicker shells or developed body shapes that made it difficult for predators to swallow them. These back-and-forth adaptations shaped the early chapters of marine evolution, long before anything resembling a mosasaur or plesiosaur ever appeared. The ocean floor supported its own communities. Soft-bodied animals burrowed into the sediment. Worm-like organisms created networks of tunnels beneath the surface. Small trilobites scuttled across the bottom, feeding on debris or hunting tiny invertebrates. These early arthropods came in countless variations, some with spines, some with large eyes, some with smooth shells. They thrived for millions of years and formed an important part of the ocean's foundation. Their behaviour helped recycle nutrients and stir the ocean floor, influencing the entire ecosystem above them. Coral-like organisms built structures too, though not always in the same style as modern coral reefs. Some ancient reefs consisted of branching sponges or colonies of organisms that grew in thick mats instead of tall structures. These reefs created safe areas where smaller animals could hide. They also provided feeding grounds for fish-like creatures that grazed on microorganisms living on the reef surface. Though different in composition, these reefs played a similar role to modern ones, anchoring life in specific regions where conditions allowed organisms to gather and feed. As the oceans continued to evolve, more modern features began to appear. True fish, with recognizable fins and streamlined bodies, slowly became more common. Some could swim faster than earlier creatures. Their mobility allowed them to hunt or escape with greater efficiency. But they didn't yet dominate the seas. That took time. The ancient oceans were still filled with creatures experimenting with body plans that didn't survive into later eras. Nature was still refining the shapes that worked best. Throughout these transitions, the world above the water influenced everything below it. Shifting climates altered temperatures. Volcanic eruptions changed chemistry. Rising and falling sea levels created new habitats or eliminated others. Continents moved, sometimes blocking the flow of ocean currents and forcing animals to adapt to new environments. Each of these changes created opportunities for some species and obstacles for others. The oceans were always in motion, not just physically, but biologically. When jawed fish continued to evolve, some developed powerful tail structures that allowed for bursts of speed. This shifted the balance again. Predators that could move quickly gained advantages over slower animals. Prey species responded by becoming faster or developing more coordinated movement patterns. This eventually led to the first forms of schooling behaviour, though not in the way seen today. Early schooling was a defensive adaptation, a way for prey to reduce the chance of being singled out. It wasn't as organised as modern schools of fish, but it served the same purpose. The development of teeth also changed the oceans. Instead of relying solely on crushing plates or simple gripping mouths, predators could slice. Teeth allowed for new hunting strategies. Some fish evolved sharp, needle-like teeth for catching slippery prey. Others developed broader teeth for cutting or tearing. These changes moved the oceans closer to the ecosystems people recognise now. But in this era, everything still felt experimental. Creature designs competed with each other, and only the most effective ones remained through time. The early oceans also saw the rise of animals that would eventually lead to sharks. These early forms didn't look much like the sleek, recognisable sharks of today. Some had strange fin placements or unusual body proportions. Some lacked the powerful jaws modern sharks possess. But their basic body plan, cartilaginous structure, multiple rows of teeth, strong swimming ability, began to emerge. These early sharks explored various shapes and sizes, with some growing large enough to become important predators in their ecosystems. As more advanced fish continued to evolve, the oceans reached a turning point. Fish with lighter skeletons, better fin control, and more efficient gill systems became increasingly common. Their speed and maneuverability allowed them to fill more ecological roles. Slowly, the oceans began to look more like the ones marine reptiles would later inherit. The groundwork was being laid for the ecosystems that would support enormous hunters like ichthyosaurs and mosasaurs. Even though this was a world where humans didn't exist, where no one watched from a safe shoreline, the oceans were already setting the stage for the creatures that would later capture our imaginations. The early fish learned how to thrive in environments that constantly shifted. Their shapes, behaviours, and adaptations formed the foundations of marine life as we know it. But before they became familiar, they lived through a time of constant experimentation, where nature tried out countless designs and only kept a few. When we imagine ancient seas, it's tempting to focus on the largest animals. But all those giants depended on the groundwork created in this earlier world. Without the endless refining of early fish, without the building of reefs, without the shaping forces that defined these first ecosystems, the later sea monsters could never have existed. Their world emerged from this long, complicated history, a history that built the foundations of the ocean long before anything even remotely human arrived to give those creatures names. By the time reptiles entered the oceans in large numbers, the world had already been through several major changes. Continents had shifted, climates had warmed, and ecosystems had expanded in ways that allowed new groups of animals to take advantage of the open water. When reptiles began to adapt to marine life, they didn't simply fill empty spaces. They reshaped entire sections of the ocean. They developed new body structures, new hunting methods, and new movement patterns, becoming some of the most successful animals ever to live in the sea. This period is often remembered for its size and spectacle, but the real story is more detailed. It's about how ordinary land reptiles gradually changed into creatures capable of dominating environments far beyond their original range. The transition from land to water did not happen suddenly. It began with reptiles that live near coastlines, often entering shallow waters to feed or escape predators. Over generations, some of these reptiles became more comfortable in the water than on land. They learned to use the buoyancy of the ocean to support their weight. They developed limbs that could paddle more efficiently. They discovered that the ocean offered abundant food and fewer obstacles than moving across rough terrain. These early adaptations created a pathway for new forms of life, and eventually some reptiles committed fully to life in the sea. One of the first groups to make this shift was the ichthyosaurs. Their early ancestors likely resembled small, slender animals with limbs that allowed them to push through sand and shallow tidal zones. Over time, their bodies grew more streamlined. Their limbs flattened and widened into flipper-like structures. Their tails strengthened into powerful vertical shapes capable of producing strong propulsion. The ocean rewarded these changes by making movement easier and faster. Ichthyosaurs eventually developed body shapes that resembled modern dolphins, not because they were related, but because the ocean tends to shape animals in ways that work efficiently. As ichthyosaurs refined their form, they specialised in hunting fast-moving prey. Their long snouts filled with sharp teeth let them snap at fish or squid-like animals with precision. Their large eyes helped them see in dim light, which was useful for diving to moderate depths where sunlight faded. Some species grew to lengths rivaling small whales, while others stayed compact and manoeuvrable. The diversity of ichthyosaurs showed how successful they were. They filled different niches and explored areas of the ocean that earlier animals couldn't reach. While ichthyosaurs occupied open water roles, other reptiles took advantage of nearshore environments. Some of these reptiles developed long bodies and strong paddles that allowed them to move through shallow water with steady control. These early forms eventually gave rise to animals like the pliosaurs. Pliosaurs had broad bodies, large heads, and strong jaws. Their limbs transformed into powerful flippers that helped them accelerate quickly. Unlike ichthyosaurs, which relied on speed and agility, many pliosaurs relied on strength and precision. Their large skulls housed muscles capable of delivering forceful bites. This made them capable of tackling larger prey, including other marine reptiles. Pliosaurs weren't the only group developing unique adaptations. Another branch of marine reptiles evolved into what people often imagine when they hear about prehistoric oceans: animals with long necks and small heads gliding through the water with flippers that moved in coordinated strokes. These were the plesiosaurs. Their long necks had dozens of vertebrae, allowing them to reach prey without moving their entire bodies. Instead of speed or brute force, they used careful positioning. by moving slowly through the water and extending their necks into schools of fish, they could grab prey without alarming the entire group. Plesiosaurs came in a variety of sizes. Some were modest, only a few meters long. Others grew massive, with necks extending far ahead of their bodies. Their movement through the water was steady and controlled. They didn't flap their flippers wildly. They used them in a coordinated, almost rhythmic pattern that allowed them to glide with remarkable stability. This method of movement let them conserve energy and remain in the water for long periods without tiring quickly. Another group that eventually entered the marine environment was the mosasaurs. Unlike plesiosaurs and ichthyosaurs, mosasaurs evolved much later, during a time when the oceans had already become dominated by reptiles. Their ancestors were land-dwelling lizards. Over generations, these lizards adapted to a semi-aquatic lifestyle and then gradually became fully marine creatures. Mosasaurs had elongated bodies, powerful tails, and jaws that could open widely. Their limbs turned into flippers, and they developed a body plan that made them effective swimmers and formidable predators. Mosasaurs were among the last great marine reptiles to evolve, and they took advantage of ecosystems that earlier reptiles had already shaped. They filled roles that ichthyosaurs had previously held, but also introduced new hunting strategies. Some mosasaurs had teeth designed for slicing, while others had teeth suited for crushing hard-shelled prey. Their skulls contained joints that allowed them to open their mouths wide enough to swallow large animals. This made them versatile predators capable of hunting a wide range of species. One of the interesting features of this era was that these major reptile groups didn't simply replace each other. For long stretches of time, they all lived alongside one another, each occupying different parts of the ocean. Ichthyosaurs dominated early on, taking advantage of warm global climates and abundant prey. Pliosaurs and plesiosaurs developed their own strategies to share the ocean without constant competition. Mosasaurs arrived later and took advantage of ecological opportunities left open as some earlier groups declined. The ocean didn't belong to a single group. It shifted through eras, with different reptiles rising in importance depending on climate, geography, and prey availability. The structure of ancient oceans played a major role in shaping these groups. During periods when continents were arranged to form wide inland seas, marine reptiles could travel incredibly far. These shallow, warm seas acted like vast highways. Animals could follow prey or escape competition by moving across entire continents. Because the environment changed gradually, reptiles had time to adapt to new conditions. This allowed them to diversify into many different forms. Food availability influenced their evolution as well. The oceans were rich with ammonites, squid-like animals with coiled shells. These creatures were abundant in many ancient seas and provided a consistent food source for predators. Fish populations grew throughout this period, and their increasing diversity created opportunities for different hunting styles. Some marine reptiles specialized in catching fast-moving fish. Others targeted slower, shelled creatures. Some animals hunted near the surface, while others preferred deeper water. The predators that lived during this era were not simply enormous animals relying on force. Many were extremely efficient in how they moved and hunted. Ichthyosaurs could reach impressive speeds. Pliosaurs had strong jaw mechanics combined with powerful flippers. Plesiosaurs used their long necks to surprise prey and avoid unnecessary energy expenditure. Mosasaurs relied on flexible bodies and strong tails for bursts of motion. Each strategy worked because the environment supported it. The ocean rewarded different approaches, allowing multiple successful designs to coexist. The relationship between predators and prey helped shape the overall structure of the oceanic ecosystem. As marine reptiles evolved sharper teeth, stronger muscles, and more advanced sensory abilities, prey animals developed new defensive traits. Some fish became faster, others formed tighter schools. Ammonites developed thicker shells or unusual shell shapes that made them harder to crack. This ongoing exchange didn't lead to a single winner. Instead, it drove the development of complexity. the ocean became filled with animals exploring new roles, adjusting to each other in ways that were stable enough to last for millions of years. Marine reptiles didn't only dominate through physical power, they also adapted in other ways. Some species developed advanced reproductive strategies. Ichthyosaurs, for example, gave birth to live young. This meant they didn't need to return to land to lay eggs, allowing them to spend their entire lives in the water. This advantage let them occupy regions that would have been impossible for animals that needed dry ground. Other species developed strong sensory organs. Large eyes, keen smell, and pressure-sensing abilities helped them navigate murky waters, detect prey at a distance, or avoid larger predators. The climate during this period also contributed to the success of marine reptiles. Many eras were warm and stable, with temperatures that made the seas comfortable for reptiles that relied on external heat to regulate their bodies. With fewer cold zones and calmer temperature gradients, marine reptiles didn't need specialized adaptations for extreme conditions. They could focus on developing hunting skills, better swimming methods, and adaptations for energy efficiency. Even the geography of the planet benefited them. Plate movements created new seas and closed others. When shallow seas spread across large areas, they provided perfect environments for reptiles to hunt, reproduce, and expand their populations. When seas receded, reptiles adapted by moving into deeper waters or shifting their diets. The constant changes encouraged resilience. Species that could adjust survived, while others vanished quietly as their environments disappeared. These reptiles filled the oceans for tens of millions of years. They became as familiar to their world as fish and whales are to ours. Their presence influenced the behavior of other animals. Their hunting strategies shaped ecosystems. Their travel patterns affected the movement of prey species. Their bodies left fossils that helped scientists piece together an era when the ocean was ruled by creatures with scales instead of fins, lungs instead of gills, and evolutionary paths shaped by land but perfected by water. And as this age continued, these reptiles spread into every part of the sea that offered enough resources. The distant open waters, the shallow inland seas, the coastal zones, and the deeper basins each held animals adapted to the specific conditions of those regions. It was a time when reptile life reached its peak in the oceans, not because they eliminated other creatures, but because they learned to use the ocean structure more effectively than any previous group had managed. As marine reptiles continued to spread through the oceans, they encountered opportunities that allowed some species to grow to sizes that seem unbelievable today. The ancient seas supported giants because the environment made it possible. Warm temperatures, abundant prey, wide migration paths, and stable conditions allowed certain animals to grow longer, heavier, and more powerful than almost anything moving through the water now. These weren't giants in the mythical sense. They weren't imagined monsters. They were real reptiles shaped by a world that rewarded size, strength, or presence in ways that don't always apply to modern ecosystems. But the ocean was not only about these enormous bodies, it also held creatures that stayed small on purpose, living in spaces where sunlight barely reached, or where larger predators couldn't maneuver easily. Together, these animals created a layered world of giant forms in open waters and smaller lives moving through the narrow or dim regions beneath them. Size in the ancient ocean didn't appear at random. It came from a combination of environmental conditions and biological opportunity. In warm periods, oceans held more oxygen and nutrients. Prey animals flourished in large numbers. With so much food available, predators could afford to grow bigger without risking constant hunger. Growing larger came with advantages. Big animals could travel long distances without tiring quickly. Their size acted as protection against other predators. They could target prey that smaller hunters couldn't reach. This created a cycle where size encouraged further size, reinforcing itself through generations. The result was a world where enormous marine reptiles became common. Some ichthyosaurs grew to lengths rivaling modern whales. These animals weren't simply long, Their bodies were thick and muscular, built for speed and endurance. Their large eyes allowed them to see in deeper water where light became faint. This gave them access to prey that stayed away from the surface, as well as areas where competition was lower. Their size also helped them regulate their temperature more effectively. Larger bodies hold heat longer, which mattered in waters that could vary slightly in temperature depending on depth or currents. These reptiles moved through the ocean with purpose, not simply as predators, but as long-distance travellers capable of crossing entire regions with steady, efficient strokes. Pliosaurs reached impressive sizes as well. These animals combined powerful bodies with massive jaws that could deliver crushing force. Their heads alone could measure more than the length of a human body. With necks shorter and more robust than those of their plesiosaur relatives, pliosaurs focused their strength at the front of their bodies. Their large flippers allowed them to accelerate quickly, making them strong ambush predators. When they approached prey, they didn't need lengthy chases. A quick burst forward allowed them to seize animals with jaws designed for gripping and tearing. Their bodies needed to be large because the prey they targeted was often big as well, including other marine reptiles. Their roles in the ecosystem relied on their ability to overpower rather than outmaneuver. Mosasaurs, which arrived later, took the concept of size in a different direction. They grew long rather than bulky, with bodies that stretched through the water like massive streamlined lizards. Their tails provided powerful thrusts, allowing them to close distances quickly. Their jaws were flexible, with hinge structures that let them open their mouths exceptionally wide. This meant they could swallow large prey or bite into animals with enough leverage to tear off substantial pieces. Their size was often combined with agility in open water, giving them a hunting style suited to environments where speed and flexibility mattered as much as strength. These giants didn't live alone in empty water. Their presence shaped the behavior of smaller animals. Many fish evolved patterns and movements that helped them avoid detection. Some relied on schooling behavior, not because it guaranteed safety, but because it made it harder for a predator to single out one target. Other prey species developed traits like rapid direction changes or the ability to blend into the background of the water. The ocean's smaller creatures responded constantly to the presence of large predators, shaping their bodies and behaviours over countless generations. But these large reptiles didn't occupy every part of the ocean. Their bulk and needs prevented them from entering certain areas. Shallow regions with coral-like structures, dense vegetation, or narrow channels weren't suitable for animals that required room to manoeuvre. Those environments belonged to smaller species that thrived in the spaces giants avoided. These areas acted as safe zones, though not completely free of danger. Smaller predators patrolled them, hunting fish, crustaceans, and other small organisms. These predators didn't need massive bodies. They benefited from agility, stealth, and the ability to dart into tight spaces. Their presence created a different kind of pressure, one built around quick reflexes rather than raw strength. Light also played a major role in dividing the ocean into distinct environments. Near the surface, sunlight was strong. It supported plant-like microorganisms and small animals that depended on photosynthesis or on feeding from brightly lit layers. This attracted many fish, and in turn attracted predators that hunted in clear, open conditions. Here, the giants often roamed, using the light to help spot prey or navigate by visual cues. Their large eyes took advantage of the brightness, allowing them to track movements from a distance. But not all animals preferred bright light. The mid-level waters held creatures adapted to dimness. In this zone, shadows stretched across the water as sunlight filtered through layers of drifting organisms. Animals in this region evolved eyes that could gather as much light as possible. Some developed sensitive lateral lines capable of detecting motion even when visibility was limited. These adaptations gave them advantages in areas where light shifted throughout the day, or where clouds and storms altered brightness. Some predators hunted specifically in these dim layers, taking advantage of low visibility to ambush prey that couldn't see them coming. Below these mid-level regions lay deeper environments where light barely reached or didn't reach at all. Here the world changed again. The water grew cooler, pressure increased, food became more scattered. Even so, life continued. Some fish evolved shapes suited to slow, energy-efficient movement. They didn't need to move quickly. They needed to conserve energy in a region where meals were less predictable. Some small marine reptiles might have descended into these depths occasionally, though few could stay long due to the pressure and cold. The creatures that lived here often had eyes adapted to faint light, or even relied on senses other than sight. These deeper regions created a form of balance in the ecosystem. They provided shelter for certain animals that didn't fit into the fast-moving world above. They also served as places where organic material from the upper layers drifted downward, providing a slow but steady food supply for scavengers. Even though the giants dominated the open waters, the ocean always maintained layers where different types of life could thrive without constant threat from larger predators. Some giants also adapted to hunt near the surface at night. Many marine reptiles likely engaged in vertical movement depending on conditions. During the day, when prey might hide deeper to avoid predators, these reptiles could travel below the light zone to search for food. At night, prey often rose toward the surface in one of the largest animal migrations on Earth, even in ancient times. This daily movement of animals changed the availability of food depending on the hour, and large reptiles likely adjusted their habits to follow these patterns. Hunting in dim or changing light required different strategies. Instead of relying solely on vision, predators might have used bursts of movement to surprise prey, or followed chemical signals in the water. Another factor in the ancient oceans was the presence of shadows cast by large animals near the surface. To smaller creatures, the silhouette of a large reptile moving overhead meant danger. Many prey species evolved the ability to sense these shadows and respond with quick dives or shifts in direction. This constant interaction between predator shadows and prey movement shaped the daily life of the ocean. The surface zones were not places of calm safety. They were fields of constant negotiation between those that hunted and those that tried to escape. Giants weren't limited to hunters. Some large marine reptiles fed on smaller prey or engaged in filter-feeding behaviours. These animals grew large because the ocean supported them with abundant small organisms. Their size allowed them to process large amounts of water or sift through rich patches of plankton or small animals. This behaviour differed significantly from the dramatic hunting scenes often associated with ancient oceans. Many of these giants spent much of their time moving slowly through fertile regions, gathering food in a steady and consistent way. Even with all this variety, size didn't guarantee dominance everywhere. Smaller predators had their own advantages. They could hide, ambush, or chase prey through areas that large reptiles avoided. They used speed instead of power. Their agility allowed them to survive in environments where size would become a disadvantage. These smaller carnivores played essential roles in controlling populations of fish, crustaceans, and other organisms. Their presence ensured that the food chain remained balanced and that larger predators had a stable supply of prey. Life in the ancient oceans was a constant interplay between scale and environment. The openness of the water invited size. The complexity of coastal and mid-level zones invited smaller shapes. Light created gradients that divided habitats by visibility. Depth created gradients that divided habitats by pressure and temperature. This combination allowed many species to coexist without overwhelming each other's niches. The giants of the deep weren't isolated wonders. They shaped everything around them, but they also relied on the rest of the ecosystem. They depended on prey populations, light conditions, water temperature, and the behaviour of smaller animals. Their size came from opportunities created by the world they lived in. Without the abundant life beneath them, they wouldn't have been able to grow so large. And the ocean, with its shifting layers and constant movement, continued to support these giants while also sheltering countless smaller species. This balance between enormous predators in open water and smaller animals hiding in dimmer layers created a world with depth, variety and complexity that defined the age of marine reptiles. It formed a foundation that set the stage for everything that would come next. Among all the creatures that filled the ancient seas, the ones that tend to capture people's attention most easily are the ones with rows upon rows of sharp teeth. Some had so many that their mouths looked more like conveyor systems for cutting than anything meant for chewing. Their teeth didn't exist for decoration or intimidation. They were tools made for a specific world. Every tooth, every jaw, hinge, and every muscle arrangement was there because something in the ocean demanded it. These animals weren't designed to frighten anyone. They evolved features that helped them survive in a place where prey moved quickly. Other predators competed for the same resources, and the environment didn't offer second chances to those that hesitated. The oceans during the age of marine reptiles were filled with creatures whose diets required different approaches. Some prey had thick shells, some had slippery bodies, some moved in bursts of speed, while others clung to the seafloor. Because of this variety, predators didn't all use the same hunting strategies. They adapted to particular challenges. That's why so many of these reptiles ended up with a seemingly excessive number of teeth. Each tooth played a role, and the arrangement of those teeth told a story about how these animals lived. Take ichthyosaurs, for example. Their teeth line their jaws in rows that seem like endless repeating patterns. They needed them because their prey, mainly fish and squid-like animals, required precision. These animals moved quickly and unpredictably. Sharp, closely packed teeth allowed ichthyosaurs to snap their jaws shut with accuracy. Their snouts narrowed into elongated shapes that let them cut through water without resistance. Their teeth didn't need to be huge. They needed to be numerous and sharp, so that even if they missed slightly, they could still catch part of their target and pull it in. Their jaws were connected to strong muscles that allowed quick snapping motions. This wasn't about crushing. It was about gripping small, fast prey tightly enough to prevent escape. In a world where prey could dart away in an instant, missing a single hunt could mean going hungry longer than was safe. Ichthyosaurs relied on efficiency, and their teeth reflected that. They weren't wasteful hunters. They were specialists designed for continuous, precise feeding in open waters. Pliosaurs, on the other hand, took a different approach. Their teeth were larger, more widely spaced, and suited for grabbing animals with thicker bodies. Their jaws needed to withstand tremendous force, so their teeth anchored deeply into robust skulls supported by strong neck muscles. These animals often engaged with prey that struggled violently, sometimes including other marine reptiles. Their teeth didn't need to be as numerous as those of ichthyosaurs. They needed to be strong enough to maintain a grip during powerful thrashing. These jaws worked more like clamps than quick-strike tools. When a pliosaur bit down, the goal wasn't simply to catch. It was to overwhelm the prey's ability to escape. Some pliosaur species developed a very pronounced tooth curvature. This curvature helped them hold on to prey more effectively, since it directed struggling animals inward rather than allowing them to slip free. This design was especially useful when hunting large prey that could twist or push back. And because these predators relied so heavily on brute force, their teeth had to withstand the pressures of heavy bites. The entire structure of their skulls reflected this need. Strong bite mechanics required reinforced bones, angled muscle attachments, and deep jaws lined with teeth shaped for penetrating thick surfaces. Another major group that contributed to the reputation of ancient oceans as places full of toothy predators was the mosasaurs. Their teeth weren't only sharp, they grew in sockets that allowed them to be replaced regularly. This kept their bite effective even after teeth were lost during hunts. Mosasaurs also developed double-hinged jaws, similar in some ways to certain modern reptiles. These jaws allowed them to open their mouths at angles far wider than many other animals of the time. Combined with their rows of pointed teeth, this allowed them to take large prey or break down substantial pieces quickly. Mosasaurs didn't rely on a single method of hunting. Some species had teeth designed for slicing. These teeth were laterally compressed, tapering to fine edges that could cut through flesh efficiently. Other species had more conical teeth suited for piercing. These were better for catching slippery animals like fish and cephalopods. There were even mosasaurs with rounded, bulbous teeth adapted for crushing shells. This variety showed how adaptable mosasaurs were. They didn't occupy just one role in the ocean. They spread into different niches, each supported by a specific dental structure. Plesiosaurs displayed yet another pattern. Their teeth were often long and interlocking, forming a cage-like structure around their jaws. This didn't create powerful bites. Instead, it created precision nets capable of catching smaller prey. Their long necks helped them extend into shoals of fish without disturbing the group. With minimal body movement, they could position their small heads in exactly the right place, opening their jaws just enough to trap prey between their interlocking teeth. This strategy didn't require massive force. It required control, patience, and a design that prevented escape without causing unnecessary damage to their own jaws. The variety of teeth among marine reptiles wasn't only about hunting. It also reflected how they processed food. Many of these animals didn't chew. They swallowed prey whole or tore pieces large enough to swallow. Chewing would have slowed them down and required jaw mechanics that didn't suit their bodies. Instead, their teeth acted as tools for grabbing, tearing, slicing, or crushing, depending on the species. Their digestive systems took on the rest of the work, breaking down food internally. Prey animals responded to these predators by developing defences. Ammonites, which were abundant in many ancient seas, developed shells of varying thickness and shape. Some shells spiraled tightly, making it harder for predators with piercing teeth to access the soft body inside. Others grew ridges or bumps that disrupted biting angles. Some fish developed armouring along parts of their bodies. Thick scales or bony plates helped reduce the effectiveness of slicing or piercing teeth. These adaptations didn't eliminate predation, but they improved survival rates. Predators had to continually refine their dental arrangements to stay effective. This ongoing interaction between predator and prey created a dynamic environment. Teeth evolved not in isolation, but as part of larger systems involving movement, sensory abilities, gut structure, and hunting patterns. A predator with excellent vision but poorly adapted teeth would struggle. A predator with strong teeth but slow movement would miss too many opportunities. Each species had to balance multiple traits, and their teeth were central to those adaptations. Some predators developed teeth that wore down quickly due to the hardness of their prey. To compensate, they evolved rapid tooth replacement. Many marine reptiles could replace teeth throughout their lives, sometimes continuously. This was essential in ecosystems where prey came with shells or hard skin that could damage teeth. Losing teeth didn't mean losing hunting ability. It simply meant new teeth would appear in their place. The placement of teeth also mattered. Some marine reptiles had teeth that extended far to the front of the jaw, giving them an advantage in striking at prey from a distance. Others had deeper set teeth designed for holding rather than reaching. The shape of the jaw influenced how teeth aligned when the mouth closed. In some species, the teeth interlocked in patterns that maximized grip. This ensured that once prey was caught, it wouldn't slip sideways or forward. In addition to teeth, the overall jaw mechanics played a crucial role. For example, mosasaurs had flexible skull joints that allowed them to adjust the angles of their jaws during feeding. This gave them a significant advantage when dealing with large or awkwardly shaped prey. Ichthyosaurs had jaws that allowed rapid closing motions, ideal for quick bites. Pliosaurs relied on sheer force generated through long, powerful jaw muscles attached to robust skulls. The oceans of the time were filled with organisms that adapted to avoid these predators. Some prey animals relied on speed. Others relied on camouflage. Some used schooling behavior to reduce individual risk. These strategies didn't only influence behavior, they influenced anatomy. Streamlined shapes protected prey from predators with slicing teeth. Flattened bodies helped animals hide near the seafloor. Bright patterns or reflective scales created confusion in light-filled waters, disrupting the aim of predators relying on sight. Not all creatures with many teeth were large. Some smaller predators also developed rows of teeth suited for their diets. These smaller reptiles or fish occupied mid-level positions in the food chain. They hunted small prey but also served as prey for larger animals. Their teeth were often fine and needle-like, designed for catching tiny, fast-moving organisms. These small predators played important roles in balancing the ecosystem. They prevented certain prey populations from becoming too large, which helped maintain stability in the food chain. The sheer number of species with specialized teeth created a complex network of interactions. This network wasn't chaotic. Each species fit into a space where their teeth served a specific function. Changes in environment or prey availability could shift these roles slightly, but the overall system remained balanced for long periods. The diversity of teeth reflected the diversity of life in the oceans. Even the birth and growth of these animals played into the structure of their teeth. Young marine reptiles often had different teeth than adults. Juvenile teeth tended to be smaller and more numerous. As the animals matured, their diets expanded and their teeth evolved accordingly. This allowed young animals to occupy different niches than their parents, reducing competition between generations. Teeth also help scientists today understand what the ancient oceans were like. Fossils preserve teeth more reliably than many other bones. Because teeth are hard and durable, they often remain intact even when the rest of the skeleton has decayed. By examining teeth, scientists can determine diets, hunting methods, and even some environmental conditions. Wear patterns reveal what types of prey were most common. The shape and size of teeth indicate how animals fed and what they likely avoided. The creatures with too many teeth earned that description not because their mouths were excessive, but because their world required those adaptations. In the oceans of the past, the interaction between prey and predator was constant. Every adaptation mattered. Every advantage increased survival chances. Teeth were central to that process, reflecting millions of years of environmental pressure and biological experimentation. Far below the giants and the smaller hunters, past the drifting layers where sunlight loses its strength, past the depths where only the faintest glimmer reaches, the ocean floor of the ancient world was constantly shifting. It didn't sit still as a quiet backdrop. It moved in slow but powerful ways that shaped everything above it. The bottom of the sea was not a fixed foundation. It behaved like a restless surface, expanding in some places, sinking in others, cracking open, pushing outward and pulling inward. And every one of these movements influenced the creatures living in the water above. The ocean floor during the age of marine reptiles wasn't the familiar map we see on globes today. Continents were still drifting into their modern positions. Huge sections of land were submerged beneath shallow seas. Ridges and trenches continuously formed and disappeared. Volcanic activity occurred not only on land but also deep under the water. These movements didn't happen quickly, of course. They unfolded over millions of years, slow enough that none of the animals living there would have recognized change within their lifetimes. But on the scale of Earth's history, the changes were continuous. That steady motion shaped coastlines, changed the depth of seas, influenced temperature patterns, and shifted the flow of nutrients. This constant motion came from processes happening within the planet's crust. Plates moved against each other. Some spread apart, forming ridges where new crust appeared. Others collided, pushing down into the mantle or rising to create mountains. Underwater ridges pushed upward to form long chains of elevated terrain on the seafloor. As new crust formed at these ridges, it pushed older crust aside, gradually widening the ocean basins. All of this movement created slopes, valleys, and ridges beneath the water, patterns that helped define where marine ecosystems could take root. One of the most influential forces came from volcanic activity. Underwater volcanoes erupted constantly during certain periods, releasing heated water, minerals, and gases. These eruptions didn't resemble the explosive events people imagine on land. Many of them were slow and steady, producing pillow-like structures as lava cooled rapidly upon contact with seawater. These volcanic regions created hot, mineral-rich conditions that supported unique ecosystems. Microorganisms living near underwater vents used chemical energy instead of sunlight, forming the base of food webs distinct from those in surface waters. These hydrothermal areas attracted small organisms and eventually larger ones that fed on the life growing around the vents. Although these communities existed far from the regions where giant marine reptiles hunted, they still connected to the broader system. The nutrients released from these volcanic areas spread outward through the water column, feeding plankton that drifted upward or outward to feed fish and other prey species. In the long chain of interactions, volcanic regions helped fuel the productivity of entire oceans. The seafloor also influenced the paths of ancient currents. Ridges, trenches, and plateaus affected how water moved. In many ancient seas, the depth wasn't uniform. Wide, shallow areas near coastlines allowed sunlight to reach the bottom, creating environments where algae, sponges, and various small organisms could thrive. Deeper regions channeled cold or nutrient-rich water along pathways sculpted by the terrain. Currents followed these contours much like rivers follow the shape of land. This movement transported nutrients and organisms from one region to another, supporting ecosystems separated by great distances. As plates shifted, entire shallow seas formed and disappeared. These seas often covered land regions that had once been dry. When the sea flooded an area, new habitats appeared almost instantly. Marine reptiles and fish moved in, taking advantage of fresh feeding grounds. When these shallow seas drained again due to tectonic changes or shifts in sea level, the ecosystems vanished, leaving behind fossils that would eventually be discovered on land. Many fossils of marine reptiles have been found far from modern coastlines for this reason. They lived in oceans that no longer exist, on seafloors now raised high above the water. Movement of the ocean floor also contributed to the rise and fall of marine species. When underwater ridges expanded, they displaced large volumes of water. This sometimes raised global sea levels. When collisions between plates created new mountains, sea levels dropped as more land rose above the water. These changes reshaped coastlines. They created new migration routes or blocked existing ones. When certain corridors widened, species could travel between different ocean systems. When they narrowed or disappeared, populations became isolated and evolved independently. During the age of marine reptiles, the presence of long inland seas created by shifts in the seafloor played a significant role in their dominance. These seas, often warm and shallow, spread across parts of continents where modern climates would never permit such environments. They served as safe, resource-rich areas where marine reptiles could feed, breed, and migrate without venturing into deep open ocean. The seafloor shaped these seas, determining where reefs formed, where sediment accumulated, and where nutrients collected. The deposition of sediment along the seafloor also affected marine life. Rivers carried soil and minerals from land into the sea, forming deltas, sandbars, and muddy basins. These sedimentary environments supported a wide variety of organisms. Some marine reptiles hunted here, feeding on fish and smaller reptiles that thrived in these nutrient-rich areas. Others avoided them because the shallow waters limited mobility for large bodies. The shape of the seafloor decided which creatures could live comfortably in certain regions and which ones needed to stay in deeper or more open areas. Even the soundscape of the ancient ocean depended on the seafloor. Movement of tectonic plates caused rumbling that travelled through the water as long, low vibrations. Underwater earthquakes, though rare on human timescales, occurred frequently over millions of years. These events helped shape trenches and basins that directed sound in different ways. Marine reptiles with sensitive hearing could detect distant movements in the water, though they likely didn't understand the tectonic sources behind the vibrations. Still, the sound of shifting plates and volcanic eruptions would have been part of the background noise of their world. Marine reptiles didn't interact directly with the seafloor often, but its constant movement influenced every part of their environment. When a new ridge formed, it changed the depth of the surrounding area. When sediment accumulated, it created a shelf where new prey species could thrive. When volcanic vents opened, they added minerals to the water that supported plankton blooms. Every motion beneath their flippers, no matter how slow, shaped the conditions that determined which species thrived. Some marine reptiles adapted to environments influenced by these changes. In shallow areas, reptiles with long necks and careful swimming patterns found plenty of feeding opportunities. Their ability to maneuver gently allowed them to reach into cracks, vegetation, or schools of fish hiding among underwater features. In deeper areas, swift predators with streamlined bodies roamed in pursuit of fast-moving prey. These hunters relied on the open water created by the shifting seafloor, taking advantage of deep basins and wide channels. The seafloor's movement also contributed to climate patterns. When large regions of the ocean floor opened up or expanded, they affected the circulation of warm and cold water. This in turn influenced global temperatures. Warm periods helped reptiles flourish across the oceans. Cooler periods altered prey distribution and forced some species to migrate or adapt. Though the animals didn't know it, these changes were tied to the shifting crust beneath the water. Reefs played a significant role as well. Ancient reefs weren't always built by corals as we see today. Some reefs formed from sponges or other organisms that created rigid structures. These reefs relied on the stability of the seafloor. When tectonic activity lowered or raised certain areas, reefs grew or died accordingly. Their presence created habitats for smaller fish and invertebrates. These animals formed the foundation of food chains that supported larger predators. Reefs also acted as barriers, altering water flow and shaping local ecosystems. As the ocean floor shifted, the availability of nutrients changed. Nutrients trapped in sediment could be released during geological upheavals. These nutrients fed plankton, which fed small animals, which fed larger predators. In this way, the seafloor acted like a slow but steady engine powering marine life. Even when changes occurred too slowly for any single animal to notice, the effects accumulated over time. Marine reptiles were highly mobile and many could travel great distances. This mobility allowed them to respond to the slow changes of the seafloor. As underwater volcanoes built up islands or ridges, marine reptiles followed prey into new territories. As basins deepened, they explored areas with different prey availability. As shallow seas dried up, they moved into remaining bodies of water. Their ability to move freely helped them thrive despite the constant motion below. The ocean floor also influenced the distribution of fossils. When sediment accumulated rapidly, animals that died in certain regions could be preserved more easily. Over millions of years, these preserved remains recorded the history of the oceans. They captured changes in species, climate, and ocean structure. Without the movement of the seafloor creating the right conditions for burial, many fossils of marine reptiles would not exist. In some areas, rapid sedimentation created layers that preserved entire ecosystems. In others, tectonic uplift brought fossils to the surface, where they could eventually be discovered. The movement of the ocean floor ensured that the story of the ancient seas was written into stone, even if the creatures themselves never saw or understood the foundation they swam above. This constantly shifting environment meant that the oceans were always in a state of transition. Even when conditions seemed stable for millions of years, the seafloor continued its slow transformations. These transformations shaped the world that marine reptiles dominated. The floor beneath them determined where prey gathered, where nutrients rose, where water circulated, and where new ecosystems formed. The oceans that supported the great marine reptiles were not still bodies of water. They were shaped by powerful, steady currents that connected distant parts of the world. These currents acted like invisible highways, carrying warm water, nutrients, and entire populations of animals across enormous distances. They moved quietly and constantly, forming patterns that repeated for millions of years. Marine reptiles depended on these currents. They followed them the way migrating birds follow air currents today. The water carried prey, distributed heat, and maintained predictable routes for travel. Without these currents, many species would have been isolated, and the world of ancient oceans would have looked very different. To imagine how these currents worked, it helps to picture the ocean not as one single mass of water, but as layers and streams moving at different depths, temperatures and speeds. Some currents travelled near the surface, pushed by winds and influenced by sunlight. Others, deeper and colder, moved slowly along the contours of the ocean floor. In the ancient world, because the continents were arranged differently, these currents moved along routes that no longer exist. But the basic forces that drove them were the same ones that drive currents today. Differences in temperature, salinity, wind, and the movement of the planet itself. The warmth of the ancient Earth played a major role. With fewer ice caps and more even global temperatures, the contrast between warm and cold water was often smaller. This created broad, slow-moving currents that could stretch across entire seas. In inland seas where marine reptiles thrived, these currents often formed circular patterns, circulating nutrients and maintaining consistent water conditions. Reptiles that hunted in these areas didn't have to deal with sudden temperature changes or strong cold water upwellings. Instead, they encountered stable pathways that made long-distance travel more efficient. Marine reptiles use these currents in ways that match their body types and behaviours. Fast, streamlined animals like ichthyosaurs could swim quickly in open water, but following a steady current allowed them to conserve energy. They didn't need to constantly fight against the flow. Instead, they moved with the water, travelling great distances without exhausting themselves. This made long migrations possible. It also helped them search for prey in new regions. If one area became less productive due to changes in temperature or prey availability, ichthyosaurs could follow a current to a different region where conditions were more favourable. Plesiosaurs, with their long necks and careful swimming style, needed predictable environments. Their method of movement didn't lend itself to rapid directional changes. The steady flow of currents let them travel without needing sudden bursts of speed. By staying within the main routes, they avoided areas where water moved chaotically or where swirling patterns made hunting more difficult. Their survival depended not only on the prey available, but also on the stability of the environment. Currents provided that stability by maintaining consistent temperature and movement patterns. Mosasaurs, which arrived later, also took advantage of these currents. Their flexible bodies and powerful tails made them strong swimmers, but even strong swimmers benefited from following the pathways created by moving water. In some regions, currents carried large schools of fish or cephalopods. Mosasaurs would follow these currents seasonally, taking advantage of temporary surges in prey abundance. Their ability to adapt to different prey types made them versatile hunters, and the currents helped distribute these food sources across large distances. The prey animals themselves often depended on currents. Many small creatures drifted passively, moving wherever the water carried them. Some fish species laid eggs that floated in the water, hatching far from their original location. This helped populate far-off regions and created food sources for predators along the way. Ammonites, which were common in these ancient oceans, used the movement of water to travel. Their shells allowed them to adjust buoyancy, and currents did the rest. This meant that predators that hunted ammonites had to track the water, not just the animals. Nutrients also travelled along these currents. Plankton, the foundation of many food chains, relied on nutrient-rich water that rose from deeper layers or moved from coastal regions. When currents brought these nutrients into open waters, plankton bloomed. These blooms attracted fish. Fish attracted predators. Entire food webs followed the patterns of water movement. Marine reptiles didn't need to understand the chemistry behind it. They simply responded to the presence of prey. Their instincts guided them along the same pathways year after year, generation after generation. These currents didn't always remain the same. The movement of continents changed their courses over millions of years. When land masses shifted, they created new pathways or closed existing ones. These changes forced marine life to adapt. Some species moved into new regions, others declined. The flexibility of marine reptiles depended on the predictability of water movement, but they also had to adjust when those patterns shifted. Their success came from their ability to sense change and respond without needing specialized adaptations for every new condition. In inland seas, currents followed different rules. These seas were isolated from the broader ocean by land barriers. Their size and shape determined how water circulated inside them. Some inland seas had slow, circular currents that carried warm, nutrient-rich water across vast, shallow areas. These regions often became hotspots for marine reptile activity because they supported abundant prey. Other inland seas developed layering, with warmer water near the surface and cooler water below. Marine reptiles used these layers based on their needs. Some hunted near the warm upper layers, others ventured into slightly cooler regions where certain prey preferred to gather. Even in shallow inland seas, the shape of the seafloor and the arrangement of coastlines influenced water movement. Narrow channels created faster currents. Wide open areas allowed slower, steady flow. Reptiles that hunted in these regions learned to use these patterns. They positioned themselves where prey was likely to travel, often near the edges of currents where moving water met stiller areas. These boundaries attracted schools of fish because small organisms tended to cluster there. Predators learned that these zones offered greater feeding opportunities. The deeper parts of oceans had their own currents. These moved slowly, following the contours of underwater mountain ranges and trenches. While most marine reptiles hunted near the surface or in mid-level waters, some might have ventured deeper, following prey, or navigating through cooler regions during certain times. The deep currents carried nutrients upward occasionally, replenishing mid-level zones and supporting the ecosystem. These upward movements weren't dramatic. They happened gradually, but over time they helped maintain stable food supplies. Currents also influenced temperature distribution across the oceans. Warm water moved from equatorial regions toward the poles, flattening temperature differences during certain ancient eras. This allowed reptiles to inhabit regions far from what would later become cold zones. Some marine reptiles extended their ranges into areas that now lie close to the modern Arctic Circle. They didn't travel there seeking extreme conditions. The water was warm enough to support them because currents transported heat across large distances. The interaction between currents and climate formed a feedback loop. Warm periods strengthened certain current patterns. Cool periods altered them. These shifts affected migration routes, prey abundance, and population distributions. Marine reptiles responded without understanding the broader forces at work. They followed the water, sensing changes in temperature or prey availability. Their ability to migrate efficiently helped them endure long-term environmental changes. Some species became highly specialized in following seasonal patterns. Prey populations sometimes moved in cycles tied to temperature, reproduction, or nutrient availability. Marine reptiles adapted to these cycles by establishing regular routes. This allowed them to arrive in the right places at the right times. Their bodies supported these long migrations. Strong flippers, powerful tails, streamlined forms, and efficient breathing systems enabled them to travel long distances without frequent rest. The shape of currents helped separate populations and create diversity. When a current split into two or more branches, groups of animals could become isolated temporarily. Over time, these groups might develop different characteristics. Some would evolve new hunting strategies. Others would adapt to slightly different water conditions. This contributed to the variety seen among marine reptiles. The oceans weren't uniform. They held subtle changes from one region to another, and those changes shaped the evolution of the creatures living there. Currents also connected different ecosystems. Water from nutrient-rich coastal areas carried essential elements into open seas. Organisms that reproduced near the shore could end up in distant waters. Marine reptiles found prey in places far from its original habitat. This connection allowed ecosystems to remain productive even when certain regions experienced declines. As long as currents continued to move, food supplies shifted rather than disappearing completely. Storms interacted with these currents as well. When strong winds pushed surface water in one direction, deeper water rose to replace it. This brought nutrients upward and stirred organisms into new positions. Marine reptiles sometimes took advantage of these events. After a storm, prey might gather in unusual areas, disoriented or relocated by the turbulence. Predators learned to search these areas, taking advantage of temporary changes in prey distribution. In regions where currents funneled into narrow passages between land masses, water speed increased. These areas became important hunting grounds. Prey concentrated there because the moving water carried food to them. Predators recognized that these choke points offered consistent feeding opportunities. They patrolled these regions regularly, using the predictable flow of water to locate prey. The structure of the land and the motion of the water worked together to create hotspots of activity. Even the reproduction of certain animals was tied to current patterns. Some species laid eggs or gave birth in areas where currents would carry young into safe regions with abundant food. The ocean did the work of dispersal. Juvenile animals didn't need to travel on their own immediately. They drifted along currents that took them to places where they could grow with minimal risk from larger predators. In this way, the currents of the ancient oceans acted as a hidden framework shaping the entire marine environment. They connected habitats, distributed life, influenced temperature, and maintained predictable routes used by creatures of all sizes. Marine reptiles did not exist apart from these patterns. They were part of them. Their lives unfolded in a world where the movement of water mattered as much as the movement of animals. Far beneath the zones where marine reptiles hunted, past the shifting layers where daylight weakens into a muted haze, there existed a realm that most of those large creatures rarely entered. The deep parts of ancient oceans weren't empty or lifeless, but they were far quieter than the surfaces above. They formed a world shaped by pressure, darkness, slow movement, and subtle patterns that few animals could sense or navigate. Even though it was distant from the dramatic hunts happening close to the light, this deep region still played an important role in the structure of the oceans. It influenced where nutrients gathered, how food chains operated, and how the entire marine system stayed balanced. In these depths, sunlight was either weak or non-existent. Without light, photosynthesis couldn't occur, so this layer didn't generate food in the same way shallower regions did. Instead, it relied on what drifted down from above. Small particles of decaying organisms, pieces of plants, discarded shells, and countless tiny organisms formed a slow, steady rain of material sinking toward the bottom. This downward flow fed the creatures that lived in the darker zones, providing a consistent, though sparse, source of nourishment. Even though the deep-water animals didn't hunt in the same way large predators did, they survived on this steady stream of falling food. Because this environment was so different from the lively, well-lit areas near the surface, the animals that lived here often looked strange compared to their surface counterparts. They didn't need the same streamlined shapes. They didn't rely on speed. Instead, they adapted to a world where movement was usually slow and energy conservation mattered more than fast reactions. Many deep-water creatures had elongated bodies, soft structures, and large eyes adapted to gathering even the smallest traces of light. Others had no need for eyes at all, living in areas where light never reached. Their senses evolved to detect vibrations, chemical cues, or small changes in water movement. Pressure also shaped life in these deeper zones. With every meter of depth, pressure increased. At certain depths, the pressure became immense, far beyond what most marine reptiles or fish could tolerate. Animals that lived here developed bodies without large air pockets. Gas-filled structures like swim bladders were often absent because they would collapse under the pressure. Instead, many deep-dwelling animals used oil-filled organs or gelatinous tissue to maintain buoyancy. Their bodies were flexible rather than rigid, able to withstand forces that would crush animals adapted for higher layers. In this darkness, the pace of life slowed. Many creatures moved with deliberate motions. Their metabolisms were slower. They didn't chase prey with bursts of energy. They waited. They filtered. They scavenged. They followed faint chemical signals in the water until they reached food sources. They didn't need large brains or complex hunting strategies. Their survival depended on patience and the ability to navigate an environment where food might be sparse but still steady enough to sustain them. Some marine reptiles may have occasionally ventured into these deeper regions, though not for long. Their bodies weren't built for extreme pressure, but they could dive far enough to reach dim zones where certain prey hid during the day. Ichthyosaurs, with their large eyes, likely took advantage of these depths more often than other reptiles. Their eyes allowed them to pick up faint outlines, helping them track prey that descended below the light during daylight hours. Even so, they couldn't survive in deeper regions permanently. They dove when needed and returned to upper layers where pressure was manageable and oxygen levels were higher. The deeper layers formed natural refuges for some species. Smaller fish hid here during the day, rising back toward the surface at night when predators were less active. This daily movement created patterns that repeated for millions of years. Marine reptiles followed these movements without fully entering the darkest depths themselves. They stayed in transitional zones where their bodies could function effectively, but the continuous migration of small prey between light and darkness connected both layers, making the deep sea an important part of the ocean's rhythm. The temperature in the deep ocean was significantly lower than at the surface. Because sunlight didn't warm these layers, they remained cool and stable. This stability shaped the lives of the creatures that lived here. They didn't experience seasonal variations in temperature as much as surface dwellers did. Instead, their environment remained consistent, with only small fluctuations caused by shifting currents or slow geological changes. This consistency meant that deep-sea animals often lived longer than their surface counterparts. Their slow metabolisms and lack of seasonal pressures allowed them to grow and age gradually. Even though the deep waters didn't host the dramatic scenes people often imagine when thinking about ancient seas, they still contained a surprising amount of diversity. Small crustaceans scuttled along the seafloor. Worm-like animals built burrows in the sediment. Soft-bodied creatures drifted slowly, waiting for falling food. Jelly-like organisms pulsed through the water with gentle motions. Some species evolved transparent bodies, making them nearly invisible. Others developed glowing organs that produced faint light, useful for communication, attracting prey, or confusing predators. These forms of bioluminescence weren't rare. In fact, they may have been even more common in the ancient oceans than in modern ones. Without sunlight, light produced by organisms became an effective tool. Some used it to lure prey, others used it to startle approaching predators. Still others displayed patterns of light to communicate with members of their own species. This glow didn't illuminate the depths. It created isolated points of brightness in a vast, dark environment. These faint lights moved slowly, like drifting signals in an otherwise silent world. The seafloor itself was covered with fine sediment formed from millions of years of sinking particles. This sediment preserved the remains of ancient animals that fell to the bottom. Over long periods, the seafloor recorded the history of the ocean above. Skeletons of marine animals, shells of ammonites, and traces of soft-bodied organisms became part of the geological record. Layers of sediment built up gradually, each one capturing a moment in the ocean's past. These layers eventually hardened into rock, preserving information that scientists would uncover millions of years later. The seafloor wasn't flat or featureless. It had hills, valleys, ridges, and trenches. Some areas were shaped by tectonic movement, others were formed by volcanic activity. Hydrothermal vents created areas of intense chemical activity. These vents released superheated water rich in minerals. Around these vents, unique communities thrived. Microorganisms used these minerals as energy sources, forming dense clusters of life in otherwise barren regions. These vent ecosystems provided food for small organisms, which in turn supported slightly larger ones. While marine reptiles rarely visited these depths, the nutrients produced by these ecosystems eventually drifted upward, becoming part of the broader ocean food web. Even the shape of the seafloor affected how water moved through these deep zones. Cold, dense water flowed along trenches and valleys, moving slowly across great distances. These movements redistributed nutrients, transported deep sea organisms, and connected different regions. Though these currents moved far more slowly than surface currents, they played a critical role in maintaining stability in the deep environment. Without them, certain regions would have become depleted while others accumulated too much organic material. In this quiet darkness, life operated on its own schedule. Predators didn't chase, they ambushed. Prey didn't rely on speed, they relied on hiding or drifting. The deep ocean wasn't a place of chaos, it was a place of steady persistence. Everything happened at a slower pace, governed by subtle cues and small energy exchanges. Even though the large marine reptiles didn't live permanently in these depths, the deep ocean influenced their world. It stored nutrients that would eventually rise to feed plankton. It protected certain species that later moved into higher layers. It preserved remains that would shape the food chain when scavengers brought pieces back upward. It acted as a sink for organic material, recycling the ocean's resources over long periods. When a large marine reptile died, its body often sank to the sea floor. In the deep ocean, that single carcass could support entire communities of organisms for years. Scavengers fed on soft tissues. Small animals burrowed into bone. Microorganisms broke down remaining nutrients. This process returned essential elements to the ecosystem, slowly supporting the growth of new organisms. The death of a giant creature on the surface became life for countless smaller ones below. The deep ocean also acted as a buffer for environmental change. When temperatures shifted at the surface, the deep layers remained stable. This stability helped maintain global temperature balance. It also protected certain species from surface-level events like storms, temperature spikes, or sudden changes in prey availability. The deep zones offered safe areas, even if they were challenging places to live. Though marine reptiles may not have understood any of this, their lives were still connected to these deeper layers. Everything that happened above was tied to the slow, constant activity happening below. The darkness beneath them held a world operating at a different pace, but it was no less important. It was simply quieter, less dramatic, steady and patient. Long before the continents took their current shapes, long before mountain ranges rose into the sky or deserts stretched across the landscape, ancient seas covered huge areas of what is now dry land. These seas didn't just sit quietly above the continents, they altered them. They eroded rock, deposited sediment, carved coastlines, built reefs, and shaped entire regions in ways that would only become visible long after the oceans retreated. The land we walk on today is full of marks left behind by waters that once supported marine reptiles, ancient fish, invertebrates, and microscopic organisms drifting in sunlit waves. During the eras when marine reptiles dominated the oceans, sea levels were often higher than they are now. Large sections of continents sank under shallow, warm seas filled with life. These inland seas stretched across thousands of kilometres, forming networks of waterways that connected different regions of the world. Animals swam over areas that today are farmland, forests, or cities. The sediment that accumulated on the floors of these seas eventually hardened into rock layers that now sit beneath our feet. One of the most important ways ancient seas shaped the land was through sedimentation. Rivers carried material from mountains and highlands into the ocean. Once the sediment reached the calm waters of inland seas, it settled to the bottom. Over time, thick layers of mud, sand, and organic remains built up. These layers recorded the history of life in those seas. They preserved bones, shells, plant fragments, and the traces left behind by animals moving across the seafloor. As millions of years passed, pressure from overlying layers compacted these sediments into rock. Mud became shale, sand became sandstone, lime-rich deposits formed limestone. These rock layers now appear on land because the continents rose, the seas drained, and erosion removed younger material from the top. Today, scientists can walk through these layers and read them like chapters in the Earth's history. They show when certain animals lived, when sea levels rose or fell, and how ecosystems changed over time. Without the ancient seas depositing these sediments, the geological record would be far less complete. Ancient seas also shaped the land through erosion. Waves rolling onto ancient coastlines wore away rock, carving cliffs and creating gentle slopes. Tides pulled sand back and forth, smoothing shorelines. Currents carried away loose sediments and redistributed them across the sea floor. Over long periods, this constant movement reshaped the edges of continents. Even after the seas retreated, the forms they created remained, influencing where rivers would later flow and where valleys would form. In many regions, the landscapes visible today, rolling hills, wide plains, layered cliffs, are direct results of ancient ocean processes. For instance, areas that were once beneath shallow tropical seas often contain limestone formations. These limestones formed from the skeletons of countless tiny organisms that thrived in warm water. When the seas evaporated or drained away, the limestone stayed behind. Later erosion sculpted it into cliffs, caves, and sinkholes. Entire geological features formed because ancient seas once existed there. Some of these seas supported vast reefs built by ancient organisms. These reefs weren't always coral-based like modern ones. Early reefs sometimes formed from sponges or other colonial organisms that built rigid structures. Over time, these reef systems grew into complex environments. When the seas disappeared, the reef structures remained, eventually becoming massive rock formations. Today, these fossilized reefs can be seen in mountain ranges or canyon walls. Their presence shows where thriving marine ecosystems once existed. Inland seas had another important role. They acted as enormous basins that collected organic material. Plants, plankton, and small organisms died and sank to the bottom. Their remains accumulated in thick layers. Under the right conditions, heat and pressure transformed these organic-rich sediments into oil, natural gas, or coal. Much of the energy used today comes from deposits created in ancient seas. The land we rely on for resources was shaped not only physically but chemically by oceans that vanished long before humans arrived. The movement of continents also influenced how ancient seas shaped the land. As tectonic plates shifted, some regions sank while others rose. When areas sank, seawater flooded in, creating new coastlines. When areas rose, seas drained away. This constant motion meant that no coastline remained permanent for long periods. Regions that were once deep underwater later became dry land. Regions that were once dry became submerged. Each transition changed the landscape, leaving behind deposits and features that marked the presence of the sea. In some places, ancient seas created layered structures that reveal their movement over time. Alternating layers of sandstone and shale indicate periods when seas advanced and retreated. Sandstone often forms in nearshore environments where waves and currents are strong. Shale forms in calmer, deeper waters. When geologists examine these layers today, they can see how many times a particular region was flooded and drained. Each cycle reshaped the land, depositing new material or eroding old layers. The fossils found in these layers also show how marine environments influenced the development of future land ecosystems. Many early land animals evolved near coastlines. These coastal environments offered access to both water and land, providing transitional spaces where evolutionary changes could take place. The presence of ancient seas shaped not only the physical landscape but the biological pathways that eventually led to the diversity of life on land. Even the distribution of minerals in modern landscapes can be traced back to ancient oceans. The evaporation of seawater in some regions left behind thick deposits of salt and other minerals. These mineral layers now lie beneath deserts or plains. In some areas, marine activity concentrated certain metals in sediments that later became valuable ore sources. The ocean didn't only shape the surface of the land, it influenced the resources buried within it. the retreat of ancient seas also exposed environments that would later support new ecosystems. When an inland sea dried up, it left behind flat plains rich in nutrients. Plants colonized these areas first, followed by animals. Over millions of years, these former seafloors became grasslands, forests, or deserts, depending on climate. In many regions, the fertility of the soil directly reflects the organic material left by the ancient marine ecosystems. Even the shapes of river pathways were influenced by ancient seas. When seas retreated, the low-lying areas they left behind became natural channels for flowing water. Rivers carved new paths through the soft sediments of former seafloors, creating valleys and basins. Today's river systems often follow these ancient depressions. Without the shape left by ancient oceans, modern watersheds would look very different. Mountain ranges also hold evidence of marine influence. Some mountains contain fossilized shells and marine sediments at their highest peaks. These peaks were once seafloor that rose due to tectonic movement. Entire sections of ocean floor were pushed upward, compressed, and folded into towering ranges. This process preserved marine fossils far above the modern sea level. Their presence in these high places shows how dramatically the land has changed since the time of marine reptiles. The presence of ancient seas influenced how life moved across continents. When certain regions were flooded, land animals were isolated. When waters drained, new pathways opened. These changes influenced migration patterns, encouraging some species to spread into areas that were previously unreachable. Marine reptiles sometimes adapted to new coastal environments created by shifting seas, influencing how different groups evolved over time. The climate also responded to the presence of ancient seas. Large inland seas affected temperature and humidity in surrounding regions. They moderated climate by absorbing heat during warm periods and releasing it slowly during cooler times. This stabilization created environments where certain plants and animals could thrive. When the seas receded, climates shifted. New ecosystems replaced old ones. Some animals moved away, others adapted. Even today, many landscapes carry the signature of ancient oceans in their structure. Rolling hills often mark former marine deposits. Flat plains indicate old seafloors. Cliff faces reveal layers of sediment laid down in ancient waters. These layers tell stories of changing depths, shifting coastlines, and the presence of creatures that swam long before any human footsteps touched the ground. The influence of ancient seas can also be seen in the distribution of modern coastlines. Some areas remained underwater for long periods, preventing the development of deep soil layers. Others emerged suddenly, forming rugged coastlines that shaped human settlement patterns millions of years later. In this way, ancient seas indirectly influenced human history. Marine reptiles swam over landscapes that would eventually hold towns, fields, forests, and mountains. They lived in waters that carved the shapes of valleys and plateaus. The land beneath these reptiles changed constantly, but their world left marks that became permanent features of the continents. For all their power, all their size, and all their adaptations, the great marine reptiles did not last forever. They thrived for millions of years across shifting oceans, changing climates, and evolving ecosystems. They adjusted to new prey, new competitors, and new environmental patterns. They survived fluctuations that would have eliminated less adaptable creatures. Yet eventually, these ocean titans disappeared. Their disappearance wasn't caused by one single event. It was the result of many factors accumulating over long stretches of time, each one placing new pressure on species that had once seemed unstoppable. The earliest signs that things were changing appeared long before the final extinction events. Ecosystems rarely collapse all at once. Instead, they shift slowly as conditions change. For marine reptiles, one of the first major pressures came from changes in the ocean itself. Sea levels rose and fell repeatedly. Inland seas that had once provided safe, warm environments shrank or disappeared. New coastlines emerged. Old coastlines vanished. These shifts created new habitats for some species, but removed vital feeding grounds for others. Reptiles that relied heavily on specific regions or prey types began to face difficulties when their stable environments transformed. Climate changes also played a major role. The warm, stable periods that supported the growth of large marine reptiles did not last indefinitely. Temperature fluctuations altered ocean currents, prey distribution, and the availability of nutrients. Some periods brought cooling, others brought warming. These changes did not always match the needs of animals that depended on steady water conditions. Reptiles capable of long migrations had some ability to adapt, but even they faced challenges as ancient currents shifted and prey moved into new territories. Another significant pressure came from the evolving fish populations. Fish continued to diversify throughout the Mesozoic era. Their body shapes became more efficient. Their movement patterns improved. Some fish species developed defensive traits that made them more difficult to catch. Others formed large schools that complicated the hunting strategies of slow-turning predators. As fish became faster and better adapted to escaping, marine reptiles had to expend more energy to chase them. This extra energy cost created subtle disadvantages that accumulated over time. The arrival of new predators also reshaped the oceans. Sharks, which had been present for millions of years, continued to evolve into more advanced forms. Their jaws became more powerful, their senses sharpened, their swimming efficiency improved. Sharks didn't eliminate marine reptiles directly, but they competed with them for prey. In some regions, sharks became dominant predators in environments where reptiles had once held the advantage. Competition does not always lead to immediate extinction, but it can slowly weaken populations by reducing available food and increasing energy expenditure. Prey availability shifted in other ways as well. Ammonites, which had been a major food source for many marine reptiles, began to decline toward the end of the Cretaceous period. Changes in ocean chemistry, sea levels, and climate affected ammonite populations. As ammonites decreased, predators that depended heavily on them had to adapt to new diets. Not all species had the flexibility to make this transition easily. Those with specialized teeth or jaw structures struggled when their preferred prey became scarce. The environment continued to change through tectonic activity. The arrangement of continents moved closer to what it is today. As land masses shifted, ocean circulation patterns were disrupted. This instability affected temperature gradients and nutrient flow. The long, warm inland seas that once supported large marine reptile populations gradually disappeared. In their place, narrower ocean basins formed, with different conditions that favoured some species over others. Reptiles that had thrived in wide, open, warm waters found fewer environments that matched their needs. Reproduction also became a limiting factor. Many marine reptiles gave birth to live young, which allowed them to spend their entire lives in the water. But giving birth required safe, stable environments. In times of greater environmental fluctuation, nursery areas became less predictable. Changes in water temperature, salinity, or prey availability could disrupt reproductive success. Even slight decreases in birth rates, if they persisted over long periods, could weaken populations. Species with slow growth or long reproductive cycles were especially vulnerable. The biggest and most dramatic factor, however, was the series of catastrophic events that occurred near the end of the Cretaceous, the same events that ended the reign of the non-avian dinosaurs on land. When a massive asteroid struck the Earth, the effect wasn't limited to the impact site. Dust and particles entered the atmosphere, blocking sunlight for extended periods. Photosynthesis slowed dramatically. Plankton populations crashed. The entire ocean food chain collapsed from the bottom upward. This collapse hit marine reptiles hard. They depended on large populations of fish, cephalopods, and other prey. When plankton diminished, small fish and invertebrates starved. Larger fish struggled to find enough food. The decline moved rapidly through the system, leaving predators with fewer and fewer resources. Reptiles that required large daily energy intake were among the most vulnerable. Their size, once an advantage, became a burden during periods of scarcity. In addition to food shortages, the aftermath of the asteroid caused rapid temperature changes. Surface waters cooled, nutrient cycles fell out of balance. The chemistry of the oceans shifted as massive amounts of material settled into the water. Acidification increased in some regions. These changes weren't gentle. They occurred on timescales far shorter than what species were used to. Even animals that had adapted to previous environmental shifts couldn't adjust quickly enough this time. The physical geography of the oceans also changed. Sea levels dropped as climates cooled. The shallow water habitats that many reptiles relied on shrank. Coastal zones changed shape. Coral-like ecosystems suffered. Areas rich in prey disappeared. Reptiles that depended on specific hunting environments lost their territories. Even species capable of travelling long distances faced difficulty finding stable feeding grounds. Competition increased during these challenging times. Sharks, which were more adaptable to varying food sources and more efficient at surviving lean periods, expanded their roles. Smaller predators with lower energy requirements endured conditions that eliminated larger reptiles. The environment had shifted towards systems that rewarded flexibility over specialization and smaller body sizes over large ones. Another factor contributing to disappearance was the reproduction rate of these reptiles. Many large marine reptiles matured slowly and produced relatively few offspring compared to smaller animals. When the environment became unstable, slow reproduction prevented populations from recovering quickly. Species that needed long periods of favourable conditions to thrive found themselves unable to replace individuals lost to starvation, predation, or environmental stress. Some marine reptiles may have been affected by changes in oxygen levels as well. When temperature changes disrupted ocean circulation, deep ocean waters could become less oxygen-rich. This affected the distribution of prey and made some regions less habitable. While marine reptiles breathed air, not oxygen from the water, they relied on ecosystems where prey could live. If prey couldn't survive due to oxygen-poor conditions, predators suffered indirectly. Though the asteroid impact is often seen as the main cause of their extinction, it is more accurate to say it delivered the final blow to groups already facing long-term challenges. Ecosystems were shifting before the impact. Food webs were becoming more complex. Competition was increasing. Environmental conditions were transforming. The asteroid simply accelerated these pressures into a cascade that the marine reptiles could not overcome. What makes their disappearance particularly striking is the contrast between their dominance and their vulnerability. For millions of years, they filled the oceans with forms ranging from agile hunters to massive giants. They adapted to temperatures, ocean currents, prey changes, and the constant motion of the seafloor. They survived events that transformed the environment many times over, yet in the end, the combined weight of climate change, ecological shifts, competition, and a sudden planetary catastrophe created conditions they could not escape. Their extinction opened ecological space for new groups of animals. Sharks increased their dominance. Marine mammals eventually entered the oceans, filling some of the same roles once held by reptiles. The oceans transformed again, just as they had done many times before. Life continued, but in different shapes and patterns. The disappearance of these ocean titans wasn't a single moment of destruction. It was a long decline punctuated by sudden shocks. It was the result of many small disadvantages accumulating until survival became impossible. Their world had supported them for millions of years, but when it changed too quickly and too dramatically, even the best adapted predators couldn't adjust fast enough. Long after the marine reptiles vanished from the oceans, long after the ecosystems they depended on transformed into new patterns, and long after the very continents they swam above drifted into new shapes, traces of their existence remained. These traces weren't left behind in bright colours or dramatic displays. They were preserved quietly in stone, sand and sediment that settled around them during their lifetimes. The marks they left behind survived because the Earth continued layering new material over the old, sealing in pieces of their world inch by inch, year by year, until entire eras were hidden beneath layers of rock. These traces didn't all look the same. Some were complete skeletons preserved in positions that suggested a final moment of stillness before the ocean floor consumed them. Others were scattered bones, separated by currents or scavengers before being buried. Many were only fragments: teeth, jaw sections, vertebrae, limb bones, ribs. Each piece carried information about the animal it once belonged to. Some fossils were so delicate that only thin impressions remained, showing the outline of scales or skin textures preserved against ancient sediment. The way these remains were preserved depended heavily on the conditions of the ocean floor. In regions where sediment accumulated quickly, animals that died had a better chance of becoming fossils. Soft mud settled gently over bodies and protected them from decay. These environments created detailed fossil records that scientists rely on today to reconstruct the appearance and behaviour of marine reptiles. In other regions, erosion or strong currents disturbed remains, scattering them before burial. These areas produced fossils that were harder to interpret, but still valuable for showing distribution patterns and evidence of ancient ecosystems. Some of the most recognisable traces left behind were teeth. Teeth preserved better than almost any other body part. Their hardened enamel allowed them to withstand pressure, mineralisation, and the passage of time. Even when entire skeletons vanished, teeth could remain intact. The shape, size, and placement of teeth provided essential clues about diets, hunting methods, and species identity. In many fossil beds, teeth are found far more frequently than bones, forming a dense record of the predators that once swam through the oceans. Vertebrae also survived well. Marine reptiles often had large, thick vertebrae that resisted decay and compression. These bones, when discovered in long series, revealed the length and structure of tails, necks, and bodies. The patterns of attachment between vertebrae helped scientists understand how these animals moved. Some species had vertebrae that allowed quick side-to-side motion. Others had structures that indicated stronger, more rigid movement. By studying these bones, scientists could reconstruct swimming styles, hunting methods, and even how certain animals may have interacted with each other. Limb bones and flippers often appeared in the fossil record as well. Though more delicate than vertebrae, these bones sometimes preserve details of muscle attachment and joint motion. The shape of flippers revealed how different species propelled themselves through the water. Long, narrow flippers suggested efficient gliding motion. Shorter, broader flippers indicated powerful strokes used for quick acceleration. Every detail helped refine the picture of what these animals looked like in motion. In some rare cases, fossils included impressions of soft tissue. These impressions captured the outlines of fins, skin textures, or internal structures. They provided information that skeletons alone could never reveal. For example, some ichthyosaur fossils preserved the outline of their body shape, showing that they had tail fins similar to modern dolphins. These discoveries helped confirm swimming styles that had only been theorized previously based on bone structure. Trace fossils also played a role in understanding ancient seas. These weren't remains of the animals themselves, but evidence of their activity. Marks left on the seafloor indicated where creatures fed, travelled, or interacted. Patterns in sediment showed where animals rested or where their flippers brushed against the bottom. These indirect signs added depth to the fossil record, revealing behavioural patterns that bones alone couldn't capture. In regions where ancient reefs existed, fossils of marine reptiles sometimes appeared embedded within reef structures. These reefs preserved snapshots of entire communities. Small organisms lived within the crevices. Larger animals swam around them. When reptiles ventured near these reefs, either for feeding or while chasing prey, they occasionally became trapped or died nearby. The reef material then covered and preserved parts of their bodies. Today, these reef fossils appear in rock formations far from the sea, raised by tectonic forces or exposed by erosion. One of the most surprising things about fossil distribution is how far inland many marine reptile remains are found. These fossils appear in deserts, mountain ranges, plains and river valleys, places that today seem completely disconnected from the ocean. Their presence in these regions shows how drastically the landscape has changed. What is now dry land may once have been covered by warm, shallow seas where marine reptiles swam freely. Over time, the water retreated and the land rose, carrying their remains along with it. In some regions, fossil beds hold evidence of entire ecosystems preserved together. There might be marine reptiles, ammonites, fish, mollusks, and plants all fossilized within the same layers. These beds reveal information about how species interacted, which prey were most common, and what environmental conditions existed. The combination of fossils paints a more complete picture than isolated remains could ever provide. Fossils also show signs of injury, disease, and life history. Bite marks on bones reveal interactions between predators. Healed fractures show that some animals survived attacks or accidents and continued living. Growth rings inside bones, similar to the rings inside tree trunks, reveal age patterns and seasonal changes in growth. These details help scientists understand lifespan, maturity, and reproductive cycles. One of the most informative types of fossils comes from animals that died shortly before giving birth or while still carrying developing young. These fossils reveal reproductive methods. In ichthyosaurs, for instance, fossils showing embryos inside the body provided proof that these reptiles gave birth to live young. This discovery changed the understanding of how marine reptiles lived and how deeply they were adapted to life in the water. Sedimentary layers themselves hold clues about the environment the fossils formed in. The grain size, colour and composition of sediments reveal whether the area was part of a deep sea, a shallow coastal region, a calm lagoon, or a rapidly moving current. Fossils found in fine-grained clay indicate calm water with little disturbance. Fossils in coarse sand suggest higher energy environments where waves or currents were stronger. These details help scientists reconstruct ancient coastlines and sea conditions. Some fossils contain mineral replacements that form detailed, three-dimensional replicas of original structures. Minerals like silica or calcite filled spaces inside bones or shells, preserving internal features that would otherwise have been lost. This process sometimes created exceptionally detailed fossils revealing structures at a microscopic level. These fossils helped identify fine features like blood vessel channels or patterns of bone growth. Even microfossils contributed to the picture. Tiny organisms such as plankton with calcium carbonate skeletons left behind millions of microscopic remains. By studying these microfossils, scientists identified climate patterns, water temperatures, and chemical conditions of ancient oceans. These patterns connected marine reptile fossils to broader environmental changes, showing how shifts in climate or chemistry influenced life in the sea. Some traces weren't biological at all. Ripple marks preserved in stone showed how waves once moved across ancient beaches. Mud cracks indicated areas that occasionally dried out. Layers of sediment with alternating textures showed seasonal changes or tidal patterns. These geological signs combined with biological fossils to form a more complete record of ancient environments. The distribution of fossils also revealed migration patterns and species diversity. When the same species appeared in fossil beds on different continents, it indicated that ancient seas had connected those regions. When species appeared only in certain areas, it suggested isolated environments or specialized ecosystems. These patterns helped scientists understand how marine reptiles moved across the world and how local conditions influenced evolution. Fossils recorded extinction as well. In some layers, diversity decreased significantly compared to earlier ones. Certain species disappeared abruptly, others dwindled slowly over time. These changes reflected the environmental pressures that eventually led to the disappearance of marine reptiles. By comparing layers, scientists could track which species disappeared first, which survived longer, and how the overall ecosystem changed. Beyond bones and impressions, chemical traces also survived. The minerals inside fossils sometimes preserved isotopic signatures that revealed water temperatures during the reptiles' lives. These measurements showed how climate changed through time and how those changes affected ocean life. Traces of organic molecules, though rare, sometimes remained locked inside fossils, offering hints about diet and physiology. The stone and sand that preserved these traces didn't remain hidden forever. Erosion, uplift, and human exploration gradually exposed them. As scientists uncovered more fossils, patterns became clearer. Each discovery added detail to the story of ancient oceans, revealing not just what marine reptiles looked like, but how they lived, how they moved, and how their world functioned. These traces don't bring the ancient ocean back, but they do allow us to reconstruct its patterns with surprising accuracy. They show how life adapted, how ecosystems changed, and how a world filled with enormous reptiles eventually gave way to something new. The story didn't vanish with the animals. It remained in the rocks beneath our feet, waiting to be found, waiting to be understood. Even though millions of years have passed since the last marine reptiles swam through ancient oceans, the sea has not forgotten them. The water that moves across the planet today is different from the water that carried ichthyosaurs, plesiosaurs, plesiosaurs, and mosasaurs, but the patterns that shaped their lives continue in new forms. The currents still move, the tides still shift, the winds still drive the surface into motion, and the creatures living beneath the waves still respond to forces that operate much the same way they did in the distant past. In many ways, the modern ocean is built upon the same framework as the ancient one. It carries the memory of those earlier worlds not through conscious recognition, but through the persistence of the systems that shaped life for hundreds of millions of years. The sea remembers through its structure. The deep trenches, broad basins, and sprawling continental shelves that define the ocean floor today were influenced by the same tectonic movements that shaped the ancient seas. The ridges that push new crust outward, the faults that pull regions apart, and the shifting plates that rearrange continents continue to operate. These geological features affect currents, temperature patterns, nutrient flow, and the overall distribution of marine life. The same slow processes that guided ancient creatures across vast distances continue to shape migration routes for modern species. The ocean remembers through its chemistry as well. The water carries dissolved minerals, nutrients, and salts that accumulate from the erosion of land and the breakdown of organisms. These chemicals cycle through the water much as they did millions of years ago. Some of the elements drifting in the sea today once passed through the bodies of marine reptiles, processed by their bones, muscles, and organs before returning to the water. At the microscopic level, the components of ancient bodies became part of the sea's chemistry, incorporated into the global cycle of elements that continues with every wave and current. The patterns of life that unfold in the modern ocean also reflect memories of earlier systems. Schools of fish still migrate along predictable routes shaped by currents. Sharks still patrol coastlines and open waters, relying on senses and hunting methods honed over countless generations. Whales travel great distances, following deep water pathways that resemble the routes once used by marine reptiles. These migrations are not conscious echoes of the past, but they exist because the underlying structure of the ocean has not fundamentally changed. The sea remembers through the continuity of its food webs. Plankton still form the foundation of life, drifting near the surface where sunlight reaches. Small fish still feed on these drifting organisms, just as ancient fish once did. Larger predators still hunt those fish, and scavengers still wait for opportunities at every level of the chain. Though the species have changed, the roles remain. The interactions that define marine ecosystems today are built on principles that shaped life in ancient seas long before humans appeared. Even the behaviours of modern animals carry faint reflections of their ancient predecessors. Some marine mammals hunt using strategies that resemble those used by long-extinct reptiles. Certain species dive through layers of darkness, following prey that rises and falls with daily cycles just as ancient creatures did. The idea of a layered ocean, bright at the top, dim in the middle, dark below, remains central to marine life today. Animals still adapt to these layers, moving in patterns influenced by temperature, pressure and light. Patterns that existed before the first plesiosaur ever glided through the water. The coastline itself acts as a memory. Many shorelines now reveal fossils that were once buried beneath ancient seas. These cliffs, riverbeds and desert exposures show the remnants of oceans that shaped the land. They hold skeletons and impressions that record how life moved through the water. The land remembers through these traces, but the sea remembers through continuity. Each wave hitting the shore today is part of a cycle that began long before humans saw the ocean as something to study, travel across, or dream about. The ocean also remembers through the survival of certain lineages. Sea turtles, for example, began their evolutionary journey during a time when marine reptiles dominated the oceans. They survived the transitions that eliminated the giants. Their shells, flippers, and lifestyles carry hints of ancient design principles shaped by earlier seas. Crocodiles and their ancestors survived the same eras, living in coastal regions affected by the same currents and ecosystems. Though they are not marine reptiles in the same sense as ichthyosaurs or mosasaurs, they experienced many of the same forces and retained structures that connect them to that past. Some fish species also preserve elements of ancient oceans. Coelacanths, once thought extinct, are relatives of ancient fish that existed during the age of marine reptiles. Their survival into modern times shows how some lineages endured while others vanished. Sharks, too, reflect continuity. While modern sharks are not the same species that swam during the time of marine reptiles, their body design, sensory systems, and ecological roles bear strong resemblance to their ancient relatives. They adapted to new environments, but their lineage remembers older patterns through the traits that allowed them to survive. Even the atmosphere influences how the ocean remembers. Wind patterns that drive surface currents today form through interactions between temperature, geography, and the rotation of the Earth, processes that shaped ancient currents as well. The cycle of warm water rising and cold water sinking has operated for millions of years, linking surface and deep layers in ways that affect both modern marine life and the fossils of creatures that once drifted down into deep waters. The memory of the ancient sea is also embedded in the sediments that lie beneath modern waves. Each grain carries the influence of past environments. Some sediments come from eroded mountain ranges that once sat near ancient coastlines. Others come from organic material left behind by creatures that lived long before modern forms evolved. As these sediments accumulate, they create new layers that future geologists will study. The process never stops. The sea continues to write its history in the same way it has done for hundreds of millions of years. When storms stir the water, they pull up deeper sediments and mix them with newer layers. This mixing connects past and present in a literal way. Particles that may have settled during the age of marine reptiles can be disturbed and carried through the water again, even if only briefly. These particles then settle once more, becoming part of modern layers that will eventually tell their own story. The ocean is a place where nothing stays completely still. Even the oldest memories shift slightly with each cycle, though the overall patterns remain recognizable. The modern ocean also remembers through its vulnerability. Ancient seas experienced dramatic changes, volcanic eruptions, climate shifts, asteroid impacts, and fluctuations that altered ecosystems. The modern sea responds to new pressures from climate change, shifting temperatures, and changes in chemical composition. While these challenges differ in their exact cause, the ocean's reaction follows the same pattern seen throughout its history. Species shift their ranges, food webs reorganize. Some creatures struggle, while others adapt. The sea continues to adjust, carrying the memory of how life has always responded to change. The ocean's persistence reinforces its memory. Despite everything that has changed, despite the loss of ancient reptiles, despite the rise of new species, despite the long passage of time, the fundamental nature of the ocean remains. Water still circulates through deep basins, sunlight still shapes the upper layers, the seafloor still moves beneath the weight of continents. Life still adapts to whatever conditions the sea provides. These patterns form a kind of continuity that connects the present to the distant past. The creatures that live in the ocean today may not resemble the giants of the Mesozoic era, but they occupy ecological spaces influenced by those earlier forms. Large predators like whales and sharks fill roles once held by mosasaurs and pliosaurs. Smaller fish and cephalopods carry out the same functions as ancient prey species. Even microorganisms drifting near the surface behave much like their predecessors, supporting food webs that depend on sunlight and nutrient cycles. The sea remembers through these recurring patterns. It holds on to them not through intention, but because the physical rules that govern its structure never stopped operating. The movements of water, the interactions between temperature and salinity, the vertical layers created by light, and the vast networks of life that depend on these systems continue exactly as they did when the first marine reptiles ventured into open water. Even the silence of the deep carries echoes of the past. In the darkest layers, where pressure is immense and light cannot reach, the quiet conditions resemble the environment that preserved so many ancient fossils. The deep sea continues to serve as a repository of remains, holding on to the traces of modern animals just as it once held the remains of the giants. Over millions of years, those remains will become part of the layers that future creatures may never see, but will eventually shape new interpretations of the ocean's history. In a sense, the sea itself is one continuous story. The characters change, the environments shift, and the details evolve, but the underlying structure persists. The ocean of today is not the same as it was during the age of marine reptiles, but it carries enough familiarity that the connection remains clear. The currents, the layered depths, the cycles of life, and the steady movement of the seafloor link the present to the ancient past.